In the last episode, I explained the basic equations for 3D rigid bodies and showed you how I implemented them in my game for a single cuboid. But who wants a game that's just made up of cuboids, right?
Let's go to a place where everything is made of blocks.
Well, okay, but I don't want to do that. I want to simulate all kinds of closed triangle meshes, like this screw thing or my wheel rim. To do that, I need to compute their inertia tensors, which is what I want to go into detail about today. So welcome to my 6th Devlog episode. Initially, I had of course no clue how to perform the computation, which is why I searched for a solution on the internet. The first useful resource I found was this paper, Fast and Accurate Computation of Polyhedral Mass Properties, by Brian Murtich, published in 1996. After checking what a polyhedron is, I thought this paper might be exactly what I need to implement, even more general than I need, because a polyhedron is a three-dimensional shape with flat polygonal faces, straight edges and vertices, as Wikipedia says. So their faces are not required to be triangles, they can have an arbitrary amount of edges or vertices, like this this thing here, which has some pentagonal faces. The input of the paper's algorithm is an object composed of potentially multiple polyhedra that each have uniform density. Also, none of the polyhedra are allowed to intersect, so they must be disjoint. And their faces must be described in counterclockwise order when looking at them from the outside. The algorithm is split up into two parts. First, it computes this inertia tensor here using just the raw x, y, z positions of every point that is part of the object's volume. They are relative to whatever origin the object was defined for. If you modeled the object like here in Blender for example, x, y and z are relative to this point. Thus, the resulting inertia tensor is relative to this origin point too. It is only useful if you'd want to rotate the object around an axis that passes through the origin. However, if you watched my last episode, you already know that rigid bodies naturally rotate around their center of mass. The x, y, z inertia tensor can't be applied here. So in the second step, the inertia tensor is transformed to express the mass distribution of the object relative to its center of mass. Instead of x, y, z, the components of r are used, which are relative to the object's center of mass. This is then the inertia tensor that we need for our rotations around the center of mass. Like the paper states, luckily, the inertia tensor doesn't need to be re-evaluated for the second step. The x, y, z inertia tensor just needs to be transformed by making use of a more general form of the parallel axis theorem, which is a constant time complexity operation. But we'll get to that later. Let's look at the first step in more detail. Because there are only integrals to be computed, which are linear over sums, the inertia tensor of the whole object omega is just the sum of the inertia tensors of its individual polyhedra omega I. So we are only concerned with the inertia tensor of a single polyhedron at a time. And since its density is constant, it can be factored out. Putting this into more of a pseudocode, the algorithm iterates over each polyhedron, then computes its density removed inertia tensor, and after that applies the density and adds the result to the final sum. The paper splits up the inertia computation into a total of 10 integrals. These 6 here are directly needed for the inertia tensor. The last row corresponds to the off-diagonal inertia tensor entries without the negative signs, while the diagonal elements are decomposed into their 3 main components, x squared, y squared and z squared. The remaining 4 integrals are for the computation of the mass itself and the center of mass, which is needed for the second step of the algorithm. Again, all of these integrals are missing the density, so this integral here, for example, actually just computes the volume of the mesh, but that is converted to the total mass by multiplying it with the density at the end. Now the question is how to perform all of these integrations over the volume of some arbitrary polyhedron. This is where the cool math happens. Because it is possible to take our volume integrals, which use every point inside of the volume of the object, and turn them into surface integrals, so that only points on the surface of the object are considered. This conversion is done using the divergence theorem. Basically, V is a region of space like our polyhedron, and del V is its surface. If V was one of the polyhedrons, then del V would be the set that contains all faces of that polyhedron. The f here is an arbitrary vector field, meaning it's just a function that outputs a vector for every point x, y, z it is defined on. The integration of its divergence over v is equal to just integrating f over the surface del v along normal direction. I am no math expert, but I think this even makes intuitive sense. If you think about the vectors that are put out by f like some sort of flow, then the divergence of this vector field at some point x, y, z tells you how much of a source or sink that point is in form of a scalar, meaning how much flow is created or lost in that point. Integrating the divergence over v gives you a net value for how much of a source or sink the whole volume is, meaning the net flow that is crossing the boundary of the volume, which is exactly what the surface integral computes. It integrates the flow in exact normal direction of the surface, so the part that is relevant for the flow in and out of the volume. If you have trouble visualizing what I just said, I would highly recommend to watch this video by 3blue1brown, which explains vector fields, divergence, and some other stuff visually. The integral reduction helps because it reduces the number of things we have to account for at once. Before, the whole volume had to be considered, but now we can just look at each phase individually and then sum the result over all phases. And while the divergence of f might look scary, it's actually really simple. It's just the sum of all components of f derived with respect to their corresponding axes. So the x output of f is derived with respect to x and so on. Since f is arbitrary, to apply the divergence theorem for each of our volume integrals, we just need to pick f in such a way that its divergence is equal to the expression we are integrating. To compute this integral, for example, the divergence of f needs to equal xy. One way to approach this is to let f of xyz be equal to 1/2 x squared y in x and 0 in x and z. Because the derivative of fx is partial with respect to x, y is like a constant here. The exponent of x is multiplied with 1/2 and reduces to 1. The result is xy for the x derivative and remains 0 for the y and z derivatives. Doing this for every one of the 10 integrals yields these surface integral reductions. Since two components of f are always chosen to be 0, the dot product with the normal vector results just in the non-zero component of f multiplied with the respective component of the normal vector. So in our example, the dot product is just this times the x component of the normal vector. To simplify it further, the 1/2 and 1/3 are constant, which means they can be factored out. And now comes the actual useful part about the reduction. The surface of the polyhedron is described by the set of its faces, so the integral can be split up explicitly to each face and all of them can be summed. The sum considers every face f of the surface and then integrates solely over f. Also, because the normal of each face is constant, the normal component can now be factored out of the face integral. What's left are these 10 simple surface integrals. To evaluate them, they are reduced even further to line integrals along the boundary of each polygonal surface. This is done using a theorem that is very similar to the divergence theorem. However, to apply that, the author first projects the 3D surfaces into a 2D plane such that the area of the projection is maximized. Then, after the reduction to line integrals, the equations are adjusted to express their values in terms of the vertex coordinates of the faces. I think the integral reduction idea is extremely cool, but as you might have noticed in the brevity of me explaining the remaining steps, I didn't make the effort to understand them in detail. They are more complicated than the first one I've shown, and also, as I saw the formulas get bigger and bigger, I always thought if I make an error converting the formulas into code, the debugging process would be a nightmare. So in midst of going through the paper, I started seeking for alternatives. However, if you want to use or implement the integral reduction yourself, not only did Brian Murtig include pseudocode at the end of his paper, he also published his ANSI-C implementation to the public domain. In addition to that, I would encourage you to look at the document Polyhedral Mass Properties Revisited, where David Eberly significantly simplifies Murtig's algorithm for the use of triangle meshes instead of polyhedral meshes. Now, the algorithm I use still looks something like this, just without the integral reduction part. So what did I do instead? Well, maybe you remember how I compute the volume of any closed triangle mesh. I covered the details of this in episode 2, but here is a short summary. The signed volume of a tetrahedron that is formed by connecting a triangle ABC to the origin can be computed using this formula. It is signed because depending on the winding order of the triangle's vertices relative to the origin, you either get a positive or a negative volume. If the winding order is consistent for a closed triangle mesh like this torus for example, then the signed volume is positive or negative depending on whether the origin lies on the back or front side of the triangle. This allows the total volume to be computed just by summing the signed tetrahedral volumes for each triangle. The volume that lies on the outside of the mesh, or the volume that would be counted multiple times, cancels with the negative volumes and only the actual volume of the mesh remains. I thought about whether this approach could be used to compute the inertia tensor of the triangle mesh, but I wasn't quite convinced. One of my professors, however, was very convinced that it was possible, so I took a closer look at it. And actually, the same paper that was referenced on Stack Overflow for the volume computation also states that the algorithm can be extended to compute the inertia tensor as well. It's the paper Efficient Feature Extraction for 2D or 3D Objects in Mesh Representation by Cha Zhang and Zuhan Chen. Here, it states that the algorithm above, which is the tetrahedron volume algorithm I explained, can also be applied to other features, such as the so-called moments of a 3D mesh model. On the second half of the page, they give an equation for these moments. Exactly what I needed. Instead of integral reduction, the 10 integrals of the Brian Murtish paper can be computed like proposed in this paper, by a sum of signed integrals over the elementary shapes, which in this case are all tetrahedrons that are formed by the surface triangle of the model and the origin. As an example, if we ignore the density rho for a second, this integral here equals to m2, 0, 0, meaning that p is 2 and q and r are 0. The other integrals can be expressed as moments too. Scrolling down to the appendix of the paper, we can even find exact formulas for the moment computation of a tetrahedron, though unfortunately it only gives formulas for the main moments. So while the integrals in the first two rows can all be computed, the bottom row here remains unknown. And because I didn't know how to integrate these expressions for arbitrary tetrahedrons, I had to seek yet another resource for that. I found explicit exact formulas for the 3D tetrahedron inertia tensor in terms of its vertex coordinates by F. Tonnen. It states the required formulas in terms of the vertex coordinates of a tetrahedron, which is really nice. And the idea of the paper is pretty interesting too. This is a slightly modified version of figure 1 in the paper. Depicted is an arbitrary tetrahedron with corners A1, A2, A3 and A4, which are in turn defined by their components x1, y1, z1 for A1 and so on. The region of space this tetrahedron occupies is called D. For our purposes, Q is any reference point relative to which the inertia tensor will be computed. It's easiest to derive a formula for the integration of a generic function f of xyz over the tetrahedron's volume, because this way there's no need to come up with a different solution for each integral we need to solve. The problem here is just that the bounds of the integration are hard to define. In the case of the centered, axis-aligned cuboid with side lengths a, b and c, it was very easy. Just integrate from the negative halved side length to the positive halved side length for each axis. But if you try to find the integration bounds for an arbitrary tetrahedron, you'd notice that it's very hard. So instead, the paper suggests to change the underlying coordinate system of the tetrahedron to this constant one, where the main coordinate axes are psi, zeta and eta. As you can see, the corner points of the tetrahedron are mapped to these very simple constant points. Either the 0 origin for A1 or 1 in any of the main axes for A1, A3 and A4, where the other components are 0. The bounds of the integration for this tetrahedron are much easier to determine. Suppose the outermost integration is in psi direction. The tetrahedron starts at psi equals 0 and ends at psi equals 1, which is why these are the bounds for psi. The consequence is that the tetrahedron is sliced up into infinitely many similar triangles. For each psi, we now need to integrate f over the area of its corresponding triangle. The paper chooses eta to be the second integration direction. While the lower eta bound is 0, 2, the upper eta bound is here. It's not 1, but instead equal to 1 minus psi, because this line here is described by psi plus eta being equal to 1. Reordering for a value of eta, we get 1 minus psi. Finally, f must be integrated along the line of a given psi and eta in zeta direction. Again, while the lower bound is 0, the upper bound lies on this plane. Reordering for a value of zeta, we get the upper bound. 1 minus xi minus eta. With all of these bounds, a function f prime that is defined on xi, eta, and zeta can be integrated. Of course, the problem now is that we want to integrate f, which is defined in the original tetrahedron space, using x, y, z instead of xi, eta, and zeta. The solution to that problem is to convert the left integral into the domain of the right tetrahedron using this substitution formula. It's the integration by substitution rule for multiple variables. D' is the domain of the normalized tetrahedron, just like D is the domain of the original tetrahedron. The function that transforms D' into D is called g in the paper. So g of D' is D. Conversely, the function that transforms D into D' is the reverse of g, not to be confused with the reciprocal of g. The substitution rule states that we can integrate f using xi, eta, and zeta in the D' domain, but we have to apply g to the arguments to convert them to x, y, and z. Additionally, the differential dd is substituted with dd' multiplied with the absolute value of the determinant of the Jacobian matrix of G at xi, eta, and zeta. If you've ever done integration by substitution in high school, this factor is basically the weird derivative thing you had to do. Just generalized and for multiple variables here, hence the Jacobian matrix. The factor accounts for the change in volume of the transformation by G. So because G might change the infinitesimal volume of each point in some different way, the result of f is multiplied with the volume factor of the differential element at that position. In our case, it simplifies quite a bit. The function g looks like this. Since a1' is 0 and mapped to a1, g adds the value of a1 to the resulting point. Starting there, each coordinate component xi, eta, and zeta just moves the resulting point along its corresponding edges in D. So xi moves along the a1, a2 edge, eta moves along the a2, a3 edge, and zeta moves along the a1, a4 edge. The Jacobian matrix in general you might remember from my second episode too. In each row of the matrix, the expression of G in the same row is derived with respect to the variable of the corresponding input domain axis of G, so xi, eta, and zeta. Inserting and simplifying, the result looks like this. Each column is just a vector from A1 to any of the other 3 points. This means first of all that the Jacobian matrix is constant and does not depend on xi, eta, or zeta, which makes it possible for the absolute value of the determinant to be factored out. Secondly, the Jacobian matrix contains the tetrahedron's edge vectors like mentioned previously. So its determinant is equal to the volume of the parallelepiped that is formed by these vectors. And that in turn is 6 times the volume of the tetrahedron D, which we'll keep in mind for later. With the previously derived formula, we now know how to specify the bounds of the D' integration. And that's the formula to integrate a function f over the volume of an arbitrary tetrahedron D. I would say if you want to know further details of the derivation, you can take a look into the paper, but what I just said was kind of already more detailed than the paper. So yeah, a compressed version of this is on page 2. The only thing left now is to replace f with the stuff we need to integrate and to solve it. Fortunately, the guy who wrote the paper did this for us. Though he didn't use the 10 integrals from Vertex paper, he used the 6 distinct values of this inertia tensor directly. The resulting formulas still look like I would make a lot of mistakes, but at least I didn't have to translate the ones that were designed for arbitrary polygons. While I was creating the animations for my last episode, I noticed that there was a mistake in my implementation that originated from the paper itself, because this inertia tensor here is actually not correct. The value of B' integrates x times z, but the outer product, which is where the off-diagonal elements come from, looks like this, where the same entry is x times y instead of x times z. It turns out the author of the paper swapped the values of B' and C'. Because C' integrates x times y, the actual value of B' instead of x times z. Whether or not this is a bug in the paper or in all of the math in Italy is up to the 10th reference, which I can't read because I neither know Italian nor can I find an accessible version of it. Nonetheless, the solution to the integrals can still be used, but we need to keep in mind to swap the result of B' and C'. Alright, no reduction of volume integrals to surface and line integrals. This is what I use to do the first step of Brian Murphy's algorithm instead. Let's take a look at my implementation. The function takes the mesh for which the inertia tensor should be computed, its constant density, and 3 pointers for the output of the inertia tensor, the center of mass, and the total mass. First, I inserted a debug check which ensures that the faces of the mesh are actually triangles and not accidentally quads or something. A nice addition to this would be to check if the mesh is actually closed and has a consistent triangle winding order, but that's a bit more complicated. Next, I declare and zero initialize all mass properties as local variables. That is the mass as a scalar, the center of mass as a vector, and the 6 distinct inertia values of the mesh as a scalar each, like in the Tonon paper. I am using double precision floats because I want the result to be more accurate. The following loop over each triangle of the mesh is really just an extension of the volume computation from episode 2. To start, I need all 3 vertex positions of the triangle. Because the mesh stores them in single precision, for each vertex I first get the native precision position and then I convert them to double precision. And now to the heart of the algorithm. The triangle P0, P1, P2 and the origin form a tetrahedron of which I compute its signed mass properties. Like we derived, the determinant of the Jacobian matrix is equal to the volume of the parallelepiped that is formed by the 3 position vectors. In episode 2, we saw that it can simply be computed with the scalar triple product. And in turn, dividing it by 6 yields the volume of the tetrahedron. Note that unlike in the Tonon paper, I use all of these values signed such that the irrelevant and double volumes cancel. With this, the tetrahedron's signed mass is just the constant density multiplied with the signed volume. The tetrahedron's center of mass is equal to its geometric center, meaning the average of the 4 points. Of course, 1 point is the origin, so there is no need to add 0 as a 4th element. I didn't provide a proof for this formula, but you could extract it from the second paper I mentioned that describes the algorithm I'm showing you right now. Like I explained in the last episode for the linear momentum, the center of mass of an object can be extracted from the integration of each of its positions, like here, such that they are conceptually multiplied with the infinitesimal masses ρ times dv. The actual result is a vector with all first-order moments as its components. It's the center of mass multiplied with the total mass of the object. Comparing this to the solution in the paper, we can see they split up in the same way. The zero-order moment is the total mass, and what remains is the tetrahedron's center of mass. The same formula I used up here. Next, I compute all 6 inertia values for the current tetrahedron according to the paper by Tonon and just add them to the local variables of the mesh. Except, of course, I keep the determinant of the Jacobian matrix signed. The diagonal elements are each composed of 2 different main moments of second order, so I wrote a function compute inertia moment which computes one of those. The off-diagonal elements are products, so I just created a function compute inertia product for that. Note that I factored out the division and density multiplication here. Also, the point x1, y1, z1 lies in the origin, so the formula in the code is a bit shorter since some of the products are 0. And because of the bug in the paper, if you were to check the formulas really thoroughly, you would notice that I add the value of c' in the paper to b' and vice versa, so these 2 indices here are swapped. After that is done, I update the center of mass and mass in a very similar way. The signedness of the center of mass comes from the multiplication by the mass. And that's mostly all there is to it. After each tetrahedron has been processed, to obtain the real center of mass, the sum needs to be divided by the total mass, and I apply the factored out multiplication and division to the inertia values according to the formulas in the paper. Finally, the inertia matrix is created like in the paper and all values are written to the pointers. Alright, now the reason that these semicolons are here and not here is because there is still something missing. The function I just went over is only step 1 of the algorithm I showed in the beginning of the video. It computes the inertia tensor relative to the origin of the mesh, meaning if the mesh was constrained to this origin and we try to rotate it, that's the inertia tensor we'd need. But unconstrained rigid bodies rotate around their center of mass, and even if they were constrained in some way, we would handle this differently. So we need to transform the inertia tensor given by this function. Conveniently, the paper by Brian Murtich also provides exact formulas to do that. They are given here on page 3. We could just copy these formulas and transform them into code, but I heard you want a bit more math today, so why don't we derive them ourselves? Let's start with the first diagonal element of the inertia tensor. To avoid forgetting brackets again, this time I'm using a mass integral directly, so no brackets needed. You can still think of it like a volume integral, but the density is included in the differential dm, which turns it into a differential mass element. This value is what we have given. It's the plane inertia relative to the zero origin. What we want is the value relative to the rigid body's center of mass, which is the case here because the respective components of the center of mass are subtracted. After multiplying out the terms using the second binomial formula, we can reorder them and apply the integrals to their individual parts. Notice that the components of the center of mass are just constants, so they can be factored out here and here together with the 2's, and here. Integrating one like this results in the total mass of the object. The other two integrals are first order moments and again just result in their corresponding components of the center of mass multiplied with the total mass of the object. After factoring out negative 2m out of both of these, we are left with negative 2 times this expression plus 1 times the same expression. The result is just negative 1 of it. So to go from our given origin inertia value to the center of mass one, we need to subtract this expression. And that's basically the parallel axis theorem, just in the reverse. Given the inertia value ICM around some axis z that passes through the center of mass, the inertia value I around the same axis passing through a different point can be computed by adding the mass times the squared distance between the two axes. In our case, the axes point in x direction and the other axis passes through the origin. So the squared distance to the same axis around the center of mass is just the squared length of the center of mass in yz direction. Also, that means we have I given and want ICM, meaning we need to subtract this expression instead of adding it, which is exactly what we derived. Comparing our result to the paper, we can see that it's the same, just a variable name for the center of mass is R. The other two diagonal elements are pretty similar, so the derivation is analogous. However, the off-diagonal elements are slightly different and I don't see how the parallel axis theorem can be applied here. So let's derive the formula for the xy off-diagonal element. Again, this is given, but we want it to be defined relative to the center of mass. Multiplying out and distributing the integral, the constant terms here and here can be factored out. And here too. As before, this constant 1 integration results in a total mass, and these two are the center of mass components multiplied with the total mass again. We are left with one addition and two subtractions of the same expression. The result is just negative 1 of it. So to go from the given inertia value to the one we want, we need to subtract this expression. And that's the formula in the paper too. The derivation of the other off-diagonal elements is analogous. Was pretty manageable, right? Turning the formulas into code is straightforward. The mass and the center of mass were already computed. For the main diagonal elements, I subtract the mass times the squared length of that part of the center of mass that is perpendicular to the corresponding main axis. For the off-diagonal elements, I subtract the mass times the product of the two relevant center of mass components. That's it. And that's the final function. To apply the code to the cuboid simulation of the last episode, I first of all needed to make some adjustments to the rigid body struct. Last time, the inertia tensor of the centered, axis-aligned cuboid was diagonal, so all three values could just be stored in a vector. This time, however, because the triangle mesh is arbitrary, its inertia tensor can be arbitrary too. The diagonal matrix assumption can't be made, which is why I now store an entire 3x3 matrix. Though it's still the inertia tensor's inverse, since that's the only form we need for the stepping of the simulation. And because it's not stored as a vector anymore, this conversion to a matrix can be removed. In setup, instead of calling the analytical cuboid inertia tensor function, I now use the triangle mesh function. I pass it the mesh of the cuboid, give it a density of for example 1, and input pointers to a matrix for the inertia tensor, a value for the total mass, and a vector for the center of mass. These last three variables will be initialized by the function. To initialize the rigid body cuboid, the mass and the inertia tensor must be inverted, since the function only returns their actual values. For the mass, this just means dividing 1 by the value. For the inertia tensor, it means inverting a 3x3 matrix, which is a bit more difficult, but still manageable. For example, when inputting a general 3x3 matrix into matrixcalc.org that has its elements already correctly indexed like they are stored in code, the inverse button will generate a solution that can be translated to code very easily. The huge denominators are all the same and equate to the negative determinant of the matrix. So computing that first, the inverse function computes the negative numerators and divides them by the determinant of the matrix. With this, the inertia tensor can be inverted and stored. And that's really everything needed to make the previous simulation work. The inertia tensor values are the same except for some tiny rounding errors that arise from the more complex method of computation. Besides testing against my previous version of the simulation, I again used the Bullet physics library to check whether my triangle mesh inertia tensor computation is correct. There are a few ways to compute inertia tensors in Bullet. First, there are exact analytical implementations for shapes like boxes or cylinders. Second, you can create a BT compound shape consisting of multiple basic shapes and compute the inertia tensor for that. Third, you can use the BT convex triangle mesh shape to compute the inertia tensor for convex triangle meshes. There doesn't seem to be any way of computing the inertia tensor for non-convex triangle meshes in Bullet, which had me wondering how people that use this library do that. After asking about it in some Discord server, it seems that they only use approximations for it. I think that's a bit strange, but at least we now know how to do better. I wrote a function very similar to mine to compute the inertia tensor for convex triangle meshes using Bullet and compared the results. This is mine and this is the diagonal of the Bullet one. They are almost the same. At first I was a bit worried about this tiny difference, but later I learned that this can be a result of a different order of operations. For example, this function produces this value on the input of some values, and this function produces a slightly different value on the input of the same values. Additionally, considering the inaccuracy of the stored vertex positions of the cuboid, I computed the exact inertia values using Wolfram Alpha and noticed that my error was even smaller than the error by Bullet, which relieved my worries. Great, the simulation works for our centered, axis-aligned cuboid with the inertia tensor computed from its actual mesh. But what if the mesh is slightly moved, such that the center of mass doesn't align with the origin? Well, this is where we run into a problem. Last episode I explained that we want the center of mass of the mesh to align with the origin. And this is what happens if that isn't the case. The computation of the inertia tensor is still correct, as you can see here. The values are almost the same as previously, just with a bit more inaccuracies. These probably arise from the fact that the mesh is now positioned further away from the origin. Since the inertia tensor is correct, the only thing we need to do is recenter the mesh to its center of mass. Like here. The center of mass is subtracted from each position of the mesh. And with that fixed, the simulation works again. Another thing I wanted to test was the computation of the off-diagonal matrix elements. So in addition to translating the cuboid, I also rotated it. Though as you can see, this is still handled without problem. My inertia tensor and the one from Bullet are almost identical again. While the simulation now starts with a slightly rotated cuboid, it still works. To test a model with a bit more triangles, I created a UV sphere with quite a high resolution and moved it off the origin again. Because this is not a cuboid anymore, I wanted to change the variable name in the code too. Instead of cuboid, it's now called RB for rigid body. Both inertia tensors were almost the same again and the simulation worked. As a final, non-convex test, I wanted to use the screw thing you saw in my last episode. It consists of a cylinder and a long cuboid attached to it. At this point, I want to emphasize the importance of the mesh triangle winding order. In Blender, you can look at the face orientation by checking this box in the Viewport Overlays menu. Since the mesh must be closed for the inertia computation to work, you should only see a blue color when looking at it from the outside. The blue color indicates that you are seeing the front side of the face. Only on the inside you should see the back side of the faces, which are colored red. In total, I have probably spent at least an hour trying to debug wrong inertia values, only to notice that they were caused by inconsistent face orientations or the mesh having holes in it. So this is very important. When loading the screw thing into the game, I couldn't really compare it to the Bullet values, because they were only meant for convex objects. So I tried to recreate it in Bullet using the cylinder and box shapes. I specified the sizes, orientations, and positions, added them to a BT compound shape, and let Bullet compute the total inertia of the object. The values were very similar, but again not quite right. The problem is that the mesh cylinder is just an approximation of a real cylinder, and the connected cuboid isn't actually a cuboid because of its connection to the cylinder. At this point though, I was happy enough. The values seemed very close to another, and I even verified the center of mass using the one calculated by Blender. Unfortunately, I couldn't find a way to get or compute the inertia tensor in Blender, so if you know of a way to do that, please let me know in the comments. To run the simulation, I modified the inertia and density parameters slightly, such that the nice turning effect appears. What remains to be fixed still is the increasing determinant of the rotation matrix. But before we can look at that, I want to change the inertia tensor in the rigid body struct back to a vector. So I want to diagonalize the matrix using the Jacobi eigenvalue algorithm. This is what we'll look at in the next episode. Lastly, if you want to use the code I presented today, I uploaded a C version of it to my GitHub. I want this repository to be a collection of all the simulation code I needed to create my physics engine, and maybe even beyond that. Which is why I'm calling it simkn for simulation collection. I chose a k instead of a c because the function prefix sk is easier to type than sc. This, for example, is the function you can use to compute the inertia tensor of a closed triangle mesh. To make it independent of any mesh structure, you pass it a void user pointer and a function that returns all three positions of the triangle at a given index using the user pointer. I want the code to be as easy to integrate into a project as possible, so it will be written entirely in C, will only use float arrays instead of custom vector or matrix data structures that you are then forced to use, and it will have lots of customization options, such as this macro for example, that lets you switch between column and row major memory layout of matrices. The C part makes the math a bit painful to work with, but that's just the problem of the one who implements the functions. Additionally, I put an MIT license on the code, so as long as you ship this license, you could even use it for commercial purposes. Though it is without warranty of any kind, of course. I might make some errors, and if you catch them or have some feedback, feel free to let me know in an issue, in the comments, or on my Discord server. Yes, since a few of you asked me, I finally decided to create one. If you want to talk about the stuff I present in my videos, have something to share that you are working on, or just want to hang out, you are welcome to join. Feedback is also greatly appreciated. An invitation link is in the video description. That's it for this episode. Unfortunately, I can't tell you when the next one will be released, because the next semester begins in a few days. I definitely want to continue, but I can't promise a regular upload schedule. Thanks for watching.